sigma is the choice of the internal three manifold. For simplicity, we can choose a Riemann surface as a closed Riemann surface, and then all the Riemann surface are characterized by the number of genus. Genus 0 surface corresponds to sphere, and the genus 1 surface corresponds to torus, and we can consider higher genuses. So similarly, we can consider compactification of the 2,0 theory along the internal three manifold. For simplest, I focus on the only for the A1 2,0 theory, which is simplest non-trivial Fokker-Field theory with n equal to 2 symmetry in the 6th dimensional, and we will compactify on the internal closed three manifolds, compact three manifolds, and the resulting theory is given by the 3D theory living on the non-compact space-time direction, and this theory will be denoted by the Tm. So this is the main hero of my talk, so please remember this notation. This theory is a three-dimensional theory labeled by the choice of the internal three manifold, and which is obtained by the compactification of a 60 2,0 theory, A1 type, along the internal three manifold. So unlike a 2D Riemann surface, so three-dimensional manifold is difficult to imagine, but fortunately there is a very well-known way to visualize three manifold, which is called the denser representation. It says that that three manifold can be visualized as this way. So we first draw a knot or link. Knot means if there is one component, that is called knot. If there are several components, it is called the link. For each component of link or knot, we associate some fractional number, which is called a slope, or it can take values in the fractional number, or it can be the infinity. Then this will define some three manifold. So one nice thing is that there is a very well-known mathematical theorem say that every closed orientable three manifold can be written in this form. So throughout my talk, I will use this convention. So if we draw knot and we could give some fractional number, then it will give some compact closed hyperbolic non-closed three manifold without any boundary. This is two examples, and so in three manifold can be labeled by in this way. So feel free to ask a question if you interrupt me if you have any questions. So
okay.
Previous,
sorry.
Yeah.
Okay. What's the meaning of P and Q? So how do you use P and Q in the surgery?
So this manifold can constructed in this way. So we consider some knot on the three sphere. Three sphere can be thought as R3 with some infinity. Then we consider this knot, and we remove tubular neighborhood of this knot. This is called knot complement. Then the resulting three manifold will have a torus boundary. Then we glue back to the solid torus this removed tubular neighborhood, and then the way of gluing back is determined by this coefficient, the PQ. So this coefficient determines how this solid is gluing back to the original, back to this tubular neighborhood. So, for example, if PQ is chosen infinity, then it already come back to this three sphere. And if we change this gluing back, the way of gluing back to solid torus, then this will give a new generate lots of the three manifold.
Okay, thank you.
Simplest example is a lens space labeled by PQ. This can be given by consider a knot, and we assign the PQ, then it will give a lens space.
But sorry, the gluing back depends on the automorphism of the surface torus, right?
Yeah. So essentially,
P and the Q must P over Q must represent a particular one, right? Is that what?
So PQ cycle, one cycle is identify another meridian of the solid torus.
Yeah.
Oh,
that's what it
I
means.
see. That's what it means. Oh.
That's what it means.
In the gluing that we should specify the SL2G structure, but it only depends the upper two components of SL2G. So this is labeled as PQ. So yeah. So yeah, the mapping class flow of torus is given by the SL2G. So to gluing, we should specify SL2G, but the resulting topology only depends on the first row column of SL2G. So it is determined by P and Q.
All right, thanks.
Thank you for the question. Yeah. So previous study studied the mostly focused on the gap list cases. For that cases, the 3D theory flowed to the spot component field theory. And then the interesting physical observers are correlation functions of local and non-local operators. So yeah, so these are the another interesting story. But in my talk, I will focus on the engineering of the gap pages. So I will ask the following questions. For which 3 manifold, the resulting 3D TM has mass gap? Then, if that the 3D TM have mass gap, how to read up the base structure of this gap page from the geometric side over the internal manifold. So in the gap page, which is described by topological field theory in 3D, the physical observers are the correlation function of loop operators. There's no non-trivial local operators, and the only important physical observer is the correlation function of loop operators. So I want to, this is the main question of my talk. So first I will determine which 3 manifold will keep a gap page, and if we keep a gap page, then how to read up this gap page, basic structure of gap page. Basically, how to compute the correlation function of loop operators in this gap page. This is interesting because that this gap page describes the more universal class of the physical system. So gap page can be appeared in the various places in physics, such as in my cases, I'm using the gap page appearing in the geometrical engineering using empire brain. But it also can be appear as some non-supersymmetric, some field theory, continuous field theory, or even it can be appear as some lattice model, which have discussed lattice. But when their theory has gaps, they all are described by the topological field theory. So in the gap case, there's no local operator, and there's no observer, which is non-trivial track acting on the non-trivial transforming on the supersymmetry. So in the gap page, supersymmetry is decoupled. So this is why that the gap page supersymmetry does not any play role, and so this gap page can describe the other universe class, which comes from the non-supersymmetric theory, even or non-relative theories, such as lattice model. So in summary, the gap page are more universal than the gapless page because supersymmetry is not important, and so this page is interesting.
So sorry, how many supercharge do you have in the TM theory?
So it have 4 supercharge generally, but if we go to the gap page, then all supercharge is decoupled, so effective theory does not have any symmetry. Yeah.
I see.
So yeah. So this UV description, empire brain left on 3 manifold will preserve 4 supercharge. But at IR, that if there is massless pages, then it will flow to the spot field theory with the 4 supercharge. But in this gap pages, this will be described by the non-supersymmetric gap page because supersymmetry doesn't act on any observers. In this way, so we can engineer, geometric engineer more universal class of the page. So this is an introduction. Let me give you some concrete example of my talk. So the gap page, the so-called some theoretical topological page can be realized in various ways. One famous example is some lattice model, which is some defined on the lattice, 2D lattice, and with the expressed Hamiltonian. And it turns out that at the zero temperature limit, where only the ground state is relevant, this system is described by some annual theory or topological theory, which is denoted by these notations. And in our setup, geometric theory, this topological page can be described by the 3 manifold on this type. Then we will show that this theory will flow to this gap page. And there's also more familiar continuum field theory description of this gapped phase, which is very simplified U1 coupled to complex scalar with a charge 2 with some superpotential. Then in this theory, there is a gapped phase, and this theory will at IR will describe the same physics. So this topological phase or some theory of anion has can be realized in various ways. So one way is the finding the condensed matter system, or is some empire brane or some continuum field theories. So this is one example that these gapped phase are universal. It appears everywhere.
So this is just a Z2 gauge theory, right?
Yeah, this is just the Z2 gauge theory.
So your continuum field theory description is a realization of the Z2 gauge theory.
Yeah, Z2 gauge theory. So symmetry is broken to U1 to the Z2 because charge 2. And then this is at the low energy, it is described by the Z2 gauge theory. Yeah, so, and this is another lattice model, so-called Turing code. And this IR, the physics of ground state is described by also Z2 gauge theory. So this is another name for Z2 gauge theory. And in my talk, this theory also can be realized as some three-manifold compactification over the Modular theory on three-manifold. Yeah, thank you for the comment. So this is the end of my introduction. Let me first explain the 3D TM theory, which is main here of my talk. So this is defined roughly. Schematically, this is defined by this one. We consider 60 Modular theory A1 type and the compact pi on three-manifold. Then at the computation, we obtained some 3D theory, which is denoted by TM. To preserve some supersymmetry, we do some partial topological twisting along the three-manifold using the SO3 R symmetry of the SO5 R symmetry. This topological twisting preserves the cut of BPS, and the resulting 3D theory generically have a 3D n equal to supersymmetry, which is the force for charge, and also has a U1 R symmetry, which comes from the SO2 subgroup of SO5 R symmetry, which is intact by the topological twisting. And there's a generic three-manifold choice. There's no other flavor symmetry. But in IR, they could have some accidental symmetry can appear in the IR. So this is a naive definition of this TM theory. There are subtle issue in the defining this theory. But this is not so important to my talk. So if you are not familiar, then you can ignore it, but let me explain it. So when we do the compactification of compact three-manifold, the resulting 3D theory is not generically not the single 3D theory, but it is some several direct sum of several different theories generically, because that in the compactification there could be some discrete component of the vacuum, and we should choose which vacuum we are compactifying. Each vacuum will give different theories. And so more precisely, so after the compactification, we are not getting some single 3D theory. Instead, we will get some collection of 3D theory, which is labeled by I. And in our choices, I choose one particular choice of the this theory, which is called usually called the irreducible component. This is called the irreducible component in the sense that if we consider this theory compacted by the S1, and the vacuum of this theory is given by the set of irreducible flat connection on three-manifold. So this is very technical, but you can just think that we are choosing some particular branch of the compactification to specify this theory uniquely. And there is also an interesting issue called the polarization choice, which is recently studied by these people. This is because that the 62,0 theory is not the theory, but it is the theory of so-called relative theory. So its theory depends on the so-called polarization choices. So depending on choices, the resulting 3D theory also depends on these polarization choices. And according to this analysis, the polarization choices are related by the choice of the subgroup of the Z2 homology of a three-manifold. So if this Z2 homology is trivial, then there is no choice of discrete choice. But if it is non-trivial, there are some discrete variant of this 3D theory labeled by choice of H, which is choice of the subgroup of this one. In my talk, in my convention, in my theories, our subgroup is chosen to be full subgroup. This is our definition. Yeah, so this is a subtle issue, but you can forget about it. But this is a precise statement of our team. So one may ask that what do we know about this theory? This is defined a very abstract theory. So first we know is that we know the effective 3D description of this theory, which is called the T3D effective. This is studied by these people. This is some gauge theoretic description, and I call this is effective low energy effective theory because that this theory, 3D theory, gauge theory, describes the same IR physics of this the 3D TM theory, which is defined this one. So this can be thought as a kind of a duality across space-time dimension. So one way to obtain this 3D TM theory is using two-major theory and the compact pi twist compact Poisson on 3 manifold. Another way to realize this 3D TM theory is that there is some gauge theory which will flow to this theory at the IR. So as concrete example, this effective theories, there is a very systematic way to construct this effective theory using some decomposition of this internal 3 manifold into the Bayesian building block, so-called ideal tetrahedron and solid torus. Here is the simple example. Suppose that the 3 manifold is given by this way. So this is a knot and some number, integer number p, and it will give us some 3 manifold. And according to Thurston, and it is known that this closed 3 manifold can be glued by gluing the 3 basic building block, 2 solid torus and one ideal tetrahedron and 1 solid torus. Then according to this algorithm, then we obtained this effective 3D theory from this gluing rule. So roughly this each tetrahedron corresponds to 1 chiral multiplet, and each solid torus corresponds to some non-abelian SO3 gauge field. So following this construction, then the effective 3D theory associated this manifold is given by simply in this way. So U1 Chern-Simon theory coupled to 2 chiral, which will flow to the CFT, which have a SU3 Flavor symmetry. Then we will gauge the SO3 subgroup of this SU3 symmetry. Then we will obtain the effective theory and this one. So in this way, so for general 3 manifold, if we know some gluing rule over using the ideal tetrahedron solid torus, we can obtain the effective 3D theory description. So this is one thing we know about this 3D theory. And another thing is that we can also compute the pattern function over some Euclidean background, supersymmetric background. So there are 2 ways to compute this pattern function. So we are interested in pattern function of this 3D theory on some curved background, which is denoted by B. Then the first thing is that we can just apply the localization technique to this effective field theory description, then we can obtain this pattern function. But there is a much simpler way to obtain this one using so-called 3D relation, which relate this pattern function, supersymmetric pattern function, to some invariant of topological invariant of internal 3 manifold. More specifically, this pattern function is related to some invariant of SL2C Chern-Simon theory on the internal 3 manifold. The choice of invariant will depend on the choice of the background, supersymmetric background we are considering. So this is the 3D relation. So in my talk, so I'm considering the supersymmetric background, which is topology given by this way, Riemann surface, degree P bundle of genus G Riemann surfaces. So many people studied on this localization on this background by these people. Using this result, we can apply local technique to this effective theory, and we can compute the pattern function, or we can also compute this pattern function using so-called 3D relation, which I will explain later. And both result always matches. So these are the two ways to compute this one. So these are the what we know about this 3D TM series. So using these two known facts, 1 and 2, we will answer the parallel question. So for which 3 manifold, this resulting 3D theory have a mass gap, and then if this theory has a gap, then how to read over base structure geometrically. This is the main question of this one, and we will use this known factor to determine the answer of this question. So do you have any questions so far?
You probably said something about it, but so are you saying, did you say that there is a relation between triangulation of the 3 manifold and the description in terms of the Dean surgery representation? Right.
Yeah, so this choice of the triangulation is related to the choice of this knot.
Mm-hmm. So
And
is that, so are you
is
saying
related
that,
to this coefficient?
so are you saying that there is an algorithm that goes between the two representations?
Yeah. So in these choices, so to use this algorithm, we should find some algorithm of decomposing into 3 manifold into Bayesian building block called the either tetrahedron and solid torus. But the way of decomposing this Bayesian building block is not unique.
Right.
And then they will give all different UV description.
Mm-hmm.
But the claim is that they all flow to the same IR fixed point. So they are all related by supersymmetry duality. So this is one way to geometrically generate all the dualities on 3D n equal 2. Not all, but the lots of class of the 3D n equal 2 can be geometric engineered in this way. Different decomposition of the solid torus and the ideal tetrahedron will give a different duality frame, and this will give a dual description. I checked that for many examples of 3 manifold, different description will flow to the same GFT field theory using the localization, but there's no general proof of that guaranteeing that this duality. But I believe that this is always true, and this will generate infinitely many basic duality of 3D n equal 2 series. But no one has studied that duality, basic duality seriously, because this is very difficult to, for given 3 manifold, finding all different triangulation or decomposition is quite mathematically different. So difficult. So this is interesting but a very challenging question.
Yeah, but mathematically, given a Dean surgery representation, can you obtain at least one triangulation?
Yeah. So given density representation, even given density representation, we can obtain the infinitely many triangulation. But the different triangulations are related by the basic move, so-called 2-3 move, and we know that what is corresponding duality in 2-3 move. So in that cases, that we know that what is the basic duality, which guarantee that this is invariant on the choice of the triangulation.
Okay.
But the most non-trivial thing is that there's no different density description, and then it is not clear that whether how can we found that these two theories actually give the same IR theory. This is quite a non-trivial duality, and I checked for many examples, it always works at the level of pattern function, but generally I don't know how to prove this.
I think his question is always not component that admits the tetrahedral decomposition. His question is.
Yeah. So at least the hyperbolic knot, it is
so large class of knot admits the tetrahedral decomposition. It's called hyperbolic knot. And
so
the example here is the simplest hyperbolic knot.
Yeah.
So that's I think large class of the knot component admits this tetrahedral decomposition. But it's not unique.
Yeah, it's not unique, and the different triangulation are related by duality. Yeah.
Thank you.
So let me try to answer this question. So for which is 3 manifold, TM mass gap, and is that. and let me try to how to read up this base structure. And the base structure of topological pairs are described by so-called modular tensor category structure. Very rigid mathematical structures. And so the final goal is that for given three-manifold, how to read up this modular tensor category structure of this resulting three-manifold, resulting depth pairs. So let me try to give the answer. So these are the main result of our work. So first, let me try to answer when this theory has mass gap. So our condition, topological condition is this: if all irreducible SL2 flat connection on M are real means that it is conjugate to SU2 or SL2R, then we will claim that the TM theory become or contain a topological field theory. For the cases with the topological field theory, we will denote it by TFMM. So if these conditions are topological conditions are satisfied, then we claim that this theory have some contain or become a topological theory. And this topological theory will be denoted by TFM and topological field theory associated M at IR. So let me explain what's the meaning of this irreducible flat connections are real. So flat connections are usually described by some SL2C Lie algebra 1 form, which satisfies these differential equations. But the simple way to describe this flat connection is using the holonomic matrices. And so using this holonomic matrix, we can mathematically define the flat connection as homomorphism from the fundamental group to SL2C up to conjugation. So this homomorphism can be constructed using these holonomic matrices. For each cycle of for each element of fundamental group, we can associate the SL2C matrix using these holonomic matrices, and this SL2C matrix should satisfy the fundamental group. So in this way, we can, from this flat connection, we can construct this homomorphism from fundamental group to SL2C. And the inverse is also true, that all the flat connection can be constructed in this way. So if we know the homomorphism of a fundamental group to SL2C, then we can automatically construct the flat connection. And a flat connection, so low alpha homomorphism is called irreducible if that all the holonomic matrices are commute. So if SL2C flat connection, low alpha is called reducible if this all holonomic matrices are commute for every element of fundamental group, and otherwise it is called irreducible. And this SL2C flat connection is called is real, which is the conjugate to SU2 or SL2R flat connection if that all the trace of holonomic matrix are real. So this is the condition. So all the elements of this are real. So let me give a concrete example of a three manifold which is satisfying these conditions. This is given by in this way. This is called the Gilbert pivot manifold. This is the density representation is given in this way. There is a four component of link, and we assign this fractional number in this way. So these three manifolds are labeled by a choice of three fractional number. And the fundamental group of this three manifold is given by this one. This can be easily read off these density representations. Some three generators with subject to these conditions. So homomorphism of fundamental group of the two SL2C can be obtained by solving these matrix equations. Just translating this fundamental relation into the matrix equation, and we obtain the homomorphism from two fundamental group to SL2C. Here, so this is a quite well-defined matrix equation, and you can solve it using Mathematica. And we can check that all the irreducible flat connection are either SU2 or SL2R by checking that all the trace matrix of these ones are real. So this is one infinite family of example which is satisfying this topology criteria. And for concretely, so when we choose this fractional number to be 3, this number, then by solving this equation, you can check that there are only the three irreducible flat connections whose holonomic matrices are expressed given in this way.
Sorry, what is the pi1 of this manifold?
This one, pi 1 over this one.
Oh, sorry, it's written there. Okay. Oh,
Yeah,
okay,
so
okay,
this
okay.
standard
Sorry.
group can be easily rid of from this density representation. Then we can solve this equation automatically using
Okay, thanks.
Yeah, then we can check that this satisfies this criteria.
Okay, thanks.
So there's at least infinity many class of 3D manifold which satisfies this topology criteria.
Sorry, can you go back one
So
slide?
let me give a
What is the alpha 0, alpha 1, alpha 2 in your example? Is it?
I just denoted the flat connection by alpha. There are 3 flat connections.
Okay.
And then I call this as alpha 0, alpha 1, and alpha 2. So for
Okay.
this manifold case.
I see. So it's 2 by 2 because it's you consider SL2C flat function.
Yeah, SL2C flat connection.
And are they real?
Sorry?
And they are real.
These are real. So in a sense, the trace of all these one are real. You can check that this trace is real and this trace is real.
Okay.
And then we can also check the trace of x1, x2, and all are real.
Okay, thanks.
And, so this is that you can check that this is real. So there's at least the infinite class of 3 manifolds satisfying this topology criteria. So let me briefly give a reasoning why that we expect that this 3 manifold have some topological phase become capped and the topology phase. This can be done by using the 3D relation for some supersymmetric pattern function on S2 times S1. Let me review the 3D relation for supersymmetric pattern function on the S2 times S1. So on S2 times S1, there are 2 distinct supersymmetric backgrounds. First one is so-called the supercomponent index, which is pattern function of S2 times S1 with the electric background for the U1R symmetry. And this can be interpreted as a canonical quantization. This can be interpreted as taking trace of the local operators. So it counts supersymmetric local operators. And another supersymmetric background on S2 times S1 is called some refined topology twist index, which is the pattern function on S2 times S1 with some magnetic background on the U1R symmetry. So this can be thought as topology twist Hilbert space on the S2. So this counts some topology twist Hilbert space ground state on this S2 topology twist Hilbert space. So one crucial difference is that this supercomponent index for supercomponent field series is the infinite power series in the Q because there's infinity many local operators, especially the local operator in CFT. On the other hand, this refined twist index is a finite Laurent series in the Q because there's only finite many ground state on Hilbert space. And this 3D relation says that this pattern function of the supercomponent index and the refined twist index in certain limit called the Carter limit, where the Q goes to 1 limit or Hava goes to 0 limit, can be written in this asymptotic expansion. And here the summation is all the irreducible SL2 flat connection on 3 manifold, and weighted by in this formal asymptotic expansion. This F0 alpha is denoted as some perturbative expansion coefficient of SL2C along this flat connection alpha. This is a classical part and this one part. So formally, this perturbative invariant, I define this one. So we are doing formal path integral over SL2C transdimensionally around some flat connection A alpha. This A alpha is a flat connection which is set by the classical equation motion. Then we can do the perturbative expansion in the formally Hava equals 0 limit. And then we can do the perturbative expansion F this way. And this F0 alpha is a classical part, and this one is one part, and two is the F2 is a true part in this way. Obviously, the classical part is just nothing but the evaluation of the classical action on this flat connection. This is Chern-Simons functional of a flat connection. And the one part is so-called the Leysinger-Reidemeier torsion, which can be led by some determinant of the Laplacian of this one. And this is very well-known topological invariant called the rational torsion, Lightman torsion. And we can also consider higher loop invariant, which is given by Fn.
Sorry, because you don't include volume because you just assume real connection or
Here,
something?
this one?
Oh,
Volume?
Volume of 3 manifold.
No, so this volume, so this, you are talking about this volume?
No, I think standard volume conjecture leading terms should be Chern-Simons plus volume, right? I times I Chern-Simons times volume.
Yeah, so this classical action is given by the Chern-Simons functional for this flat connection.
Okay.
And so if we are considering hyperbolic manifold, there is some
contains
special flat connection, which is can be constructed by hyperbolic structure.
Okay.
And if we evaluate this Chern-Simons functional on this hyperbolic flat connection, then we obtain the volume and the Chern-Simons term.
Okay. Thanks.
Yeah. So these are the perturbative invariant, and this is the one loop invariant and so. So this 3D relation says that this Spokova index in the Carter limit can be written in this form, can be written as a summation of the flat connection with weighted by this one and this one. So in Spokova index, this limit is singular because there is a 1/2 atom. This reflects that this is infinite power series in Q half. So Q = 1 limit is a singular limit. On the other hand, this twist index, this Haber-0 limit is well defined. This also reflects that this is a finite Laurent series in Q half because that Q = 1 limit is well behaved. So these are the 3D relation for two supersymmetric background, which is studied by Kite recently. And then using this 3D relation, we can argue that this claim for when 3 manifold sets of this condition, then all the flat connections are real. So it means that all flat connections are real. It means that all perturbative invariant of associated flat connections are also real. So it means that this Spokova index and the defined twist index should be the equal, because that you can see that if these are real, then there is cancellation here, and this will become same as this one, and this will become this one. So this topological criterion imply that according to 3D relation that this theory has a Spokova index is same as topological twist index. But recall that for supersymmetric theory, Spokova field theory cases, Spokova index is infinite power series. On the other hand, the topological twist index is a finite Laurent series. The only physical reason that the two quantity become same is that this theory follows the topological theory. On the topological theory, Spokova index trivially become 1 because there is no local operators except the trivial identity operators. And the topological twist index also become 1 because that there's only one ground state on two sphere for topological field theory. So this is the only way to explain the equality between the Spokova index and the defined twist index. So we claim that from this argument that if these 3 manifolds that's by this condition, then the resulting 3D theory should be topological theory. In a sense that the Spokova index becomes trivial. There's no non-local operators. But this reasoning has some loophole when the theory have some accidental abelian symmetry. Then if there is an accidental abelian symmetry, then Spokova index depends on the additional parameter called mu and u. So mu is some additional parameter fugacity variable for associated this additional symmetry, and the mu is the parameter parameterizing the R symmetry mixing between the UV R symmetry and some enhanced additional R symmetry. And the correct choice of the mu should be determined by so-called F maximization. But the 3D only can say is that cannot see this additional symmetry. This 3D index only can say that when the choice there's no mixing and this stochastic will give 1. So this 3D conclusion only can say that this supercompactor index at this choices just become trivial for when the 3 manifold satisfy this one. So if there is additional symmetry, the supercompactor index is not generically not trivial, but only this subsector, this topological supercompactor index become 1. This is the conclusion from the 3D relation. In these cases, we will interpret that this topological theory is live in this 3D theory at some degenerate limit. When this theory is not flow to topological theory, but this theory is flow to CFT with the U1 flavor symmetry, which contains this topological theory as a subsector. This is our interpretation. So we will come back to this point later. So this is one of our main results that if all the irreducible flat connections are real, then we will claim that this theory will become a topological theory or it contains a topological theory. Then the next question is that how to determine the basic structure of a topological space from the geometrically. So for simplicity, we will first consider some 3 manifold which have a trivial Z2 homology. In these cases, then the resulting 3D theory is described by just the bosonic topological field theories. And we will come back to some general cases later. And this topological field theory, then this basic structure of topological field theory is determined by the modular tensor categories. And one subset of information of the modular tensor category is encoded so-called the modular structure of a topological space, and which is basically some S and T matrices. And this is a dictionary to obtain this modular structure of this topological space from the geometric side. So this topological theories, the basic objects are so-called the anion, which is loop operators. And the first thing we should decide over this theory is that what kind of type of anions are allowed in this theory. So these anions are labeled by alpha. In my case, this runs from 0 to the n-1. This n is the so-called length of this topological space. And in the dictionary, this the length of the topological theory is determined by is one-to-one with the irreducible flat connection on the internal 3 manifold. So anions, so type of loop operators are determined by there is a one-to-one correspond with the irreducible flat connection on the 3 manifold. And in topological theories, so these loop operators called the anions. So anion has some quantum numbers, so-called the quantum dimension and some topological spin. And these quantum dimensions and the topological spins are determined by this torsion and the transformer functional. And these quantum dimensions are encoded in the S matrices, and these S matrix quantum dimensions are determined by the torsion of these flat connections, which is, as I told you, this is one part of this flat connection. And this topological spin are determined by this transformer functional. So if we find some flat connection over 3 manifold, then it will determine the contents of the anions. And if you compute the torsion and the transformer functional, then it can determine this quantum dimension of the anion and the topological spin of this anion.
I have one question. So from this, like a T of M theory, so you can determine only the zeros component of S matrix. Can you determine full S matrix?
Yeah, so this full S matrix can be determined in the last line.
Sorry. Thanks.
Yeah, using that. Yeah. So and the full determine this topological spin, we should also specify which flat connection correspond to the trivial anions. So among these anyons, there is so-called trivial anyon, which correspond to trivial loop operators. And then this trivial anyon can be determined by this criterion. And as Satoshi mentioned, this only determine the first component of S matrix, but the full S matrix can be obtained by so-called flat connection to loop operator map, which I explained later. So this is one of the main results of our paper, which can lead up the modular structure of topological space using the topological invariant of a 3-manifold.
Sorry?
Yeah.
So here the anyon is a finite dimensional representation. The
Sorry?
TFT. TFT is the anyon is a finite dimensional.
Yeah.
So
Yeah,
how could you explain how to associate with the torsion of the representation flat connection? Rho A is associated with quantum dimension.
Yeah, I will explain later. Yeah, I will explain. This is a result, and I will explain this how to derive this one.
Okay, thanks.
Yeah, so these are anyon finite set, and some identical flat connection on the flat connections are also some manifold cases are finite cases, and then this dictionary only works that there is only finite number of identical flat connection on the 3-manifold. And for each flat connection, we can consider torsion and the transient invariant, and it will determine this quantum dimension of anyon and topological spin. And the full S matrix can be determined by this so-called flat connection to loop operator map, which I will present later.
Thanks.
Yeah. First, let me explain what is the modular structure of topological space. So let me explain what is the modular structure of topological space. So in topological space, the only loop physical observers are so-called the loop operators, and for simplicity we consider loop operator on two torus. And then the loop operators are labeled by two types. One is the choice of the one cycle on torus, which is gamma. Gamma is the element of one cycles, and alpha is the labeling the type of loop operators. And this type of loop operator also contains a trivial loop operator, which corresponds to alpha equals 0 cases. Alpha equals 0 corresponds to loop operators. So depending on the topological theory, that allow the loop operator different. And this, depending on the topological theory, this allow the loop operators labeled by 0 to the n-1. And this number of n is called the length of a topological space, which is basic, one of the basic invariant of a topological space. And one nice thing is that this ground state or Hilbert space can be parameterized by these loop operators. It is because that there is all the Hilbert space can be excited by the loop operators. There is some trivial vacuum, and then we can act on the loop operators along the B cycle. Then it will generate all the Hilbert space, which are actually the ground state for topological space. So this anyon can be thought in two different ways. One is the labeling of the loop operators, or can be alternatively can be thought as some parameterizing the ground state on torus, because that all the ground states are labeled by the excitation of the loop operators. And these loop operators acting on this Hilbert space, this Hilbert space. And since these loop operators are labeled by the one cycles, and on the one cycle there is a natural SL2G action on the torus. And so this SL2G action, modular transformation on torus, will generate some SL2G transformation on this Hilbert space. This operator is called the pi hat, which is associated to SL2G matrix. Then the S matrix and T matrix are nothing but this element of this S and T matrix. For SL2 transformation K series, so this S and T matrix are given in this way. And this alpha labeled the Wilson loop representations, which are truncated this way. So modular data contains a lot of information of this topological space. First, that the ground state degeneration of topological space can be computed using so-called Berlin formula in this way. If you know the S matrix, then we can compute the ground state degeneracy. And so topological spin of the topological anyons are encoded in the T matrices. And the fusion coefficient also can be computed using some so-called another Berlin formula using the S matrices. And also another Paschen function Euclidean space can be computed using S matrix, such as the ground state degeneracy can be regarded as a Paschen function on the Riemann surface times S1 can be written as this S matrices. And this S matrix can be thought as a Paschen function of the topology theory on S2 with this kinds of a link, alpha type and the beta type along the Hopf link. And more generally, some topological Paschen function on this degree P bundle of a Riemann surface can be computed by this S and T matrix, summing over this alpha data. So in this way, so this modular data contains a lot of information about topological space. But it turns out that this it is not incomplete in the sense that this if you want to compare the Paschen function of a 3-sphere with this knot link with it's called heightened link with alpha type and beta type, and this cannot be determined by this modular structure. And actually, there's this two CFT, distinct CFT. There exists two distinct CFT which have the same modular structure but different. This Paschen function is studied by quite recently in this way. So this modular structure is not is compared to distinct topological space, but it still contains a lot of information. So far I explained that for given topological space, there is some modular structure which is by S and T matrix, which is n by n matrices. The reverse engineering, we can classify the possible topological space by classifying all possible modular structures. And this S and T matrix should satisfy some consist conditions, this kind of conditions, including the unitarity conditions, which is imply that all the quantum dimensions should be positive, bigger than 1. Then this condition, from solving these conditions with some additional condition, we can try to classify all the possible values of S and T matrices. This is somewhat similar to the component bootstrap to classify topology, supercomponent field theories. And as a result, people found that classified all the Geometrical topology space possible S and T matrix up to rank 4. This is
what are the H1 to Hn?
H1 to Hn is a topology spin of the anyons.
Oh, I see.
So this is a rank 1. It means there's only one anion, and this anion has a spin 0. And this is the rank 2, and there are 2 anions, and whose topology spins are given this way. And these are the classified. So
okay, thanks.
Yeah, this is the topology spin data encoded in these T matrices. So if you classify all the S and T matrix, you can obtain this vector. Yeah. So these are the information of the how to read of this modular structure of topology page on this one.
Sorry?
Yeah.
Is any minimal model realization for this anion?
Sorry?
So is there any two-dimensional minimum model to realize such kind of the anion?
Yeah, if there is a 3D topological theory that at the boundary there lives a chiral some CFT, and so if the topology space, then we can also associate the chiral some CFT, rational CFT, and this modular structure of S and T matrix of rational CFT is the same as this modular structure of topology space. So minimal model can be also realized as some rational CFT. So
right.
So this, and they live at the boundary of this topological space.
Right.
So in this way, so classification of topological space is somewhat related to the classification of the 2D rational CFT.
Okay, thanks.
Yeah.
So then, sorry. So do minimal models actually appear in the table of Shogun-Wen?
Yeah, I think that
I don't
yeah,
think so.
some theory such as I don't know. So minimal model,
Ising model. Yeah.
yeah, Ising model also, yeah, Ising model such a, yeah, this kind of Ising model can be realized there. Yeah. So there are three, yeah.
But
Three
other
critical.
minimal models. How about other minimal models?
Yeah, I think other minimal model also should be yeah, should be appeared in the classification, but this is only up to rank 4. So if you increase the up to rank 4, for simplicity, I present only rank 4. And so yeah, I think that the yeah higher.
Actually, so A1, A2, A3, D4, do they correspond to minimal models?
I'm not sure. Yeah.
Okay.
Yeah. 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 This is some S3 Chang-Simon series level 1. Yeah. Something like this one. This is a S3 Chang-Simon series level 1, and this is S4 Chang-Simon series level 1. Right.
Okay.
So let me explain how to derive this dictionary, and this is using the so-called 3D3 relation. So for this covered background. So 3D3 relation roughly related the Bachan function superposition the Bachan function on the covered background to the some SL2C Chang-Simon invariant of internal manifold. So the simplest the 3D3 relation is when the 3 manifold is chosen in this way. So this is a degree P bundle of a genus G-Riemann surfaces. Then the corresponding quantity, topological quantity on the 3 manifold is simply given by in this form. So summation of all the irreducible flat connection weighted by this one, torsion, and this is one part of flat connection and the Chang-Simon function. And recall that this torsion part appears the one part associated with the flat connection, and this Chang-Simon part appears the classical part. So this dictionary is the simplest dictionary because that only the classical part and the one part appeared on the right hand side of the 3D relation.
A question?
Yeah.
How do you obtain this formula?
This is yeah, derived from this one. There's two ways that the yeah, what I did in this paper is that I know the filter series description, and I applied the localization technique to compute this Bachan function.
So you're saying localization?
Yeah, I know the localization, how to compute the Bachan function, and because that we know the effective filter series description of TM. So for even 3 manifold, we can compute this Bachan function using localization. And then I compared this right hand side using 3 manifold, and I found that these are matches. So this is one way how to derive this 3D relation. And there's all other way to derive 3D relation, which I will skip. Yeah. Yeah.
I see.
So when
Yeah,
G
so-
G equals to 0 and P equal to 0, you get the 1.
Yeah. G equals 0 and D equals 1. Yeah, so this formula is quite non-trivial. So if we know that G equals 0 and the P equals 1, this compute the ground state degeneracy of S2 times S1.
Yeah.
And if we topological theory, it should be 1. But
Yeah.
in this computation in the right-hand side, this is not obvious because that the issue sum of
Sum of a torsion, right?
Torsion.
Yeah.
But it turns out that it always become 1, non-trivially.
Oh, I see.
So this is a kind of the new kinds of new mathematical conjecture. So if it satisfies 3 manifold satisfies certain condition, then this right-hand side for G equals 0 and P equals 1, P equals 0 should be always 1.
And
So
which
the
manifold does it satisfy this property? Which T of M, T of M theory satisfy this real condition, or this S1 cross S2 is equal to 1?
Yeah, so if the 3 manifold satisfy this condition, all the irreducible frequencies are
No,
real.
I understand. Which manifold satisfy this condition? I'm asking.
We don't know the full classification, but we know the infinite many class of 3 manifold. One is this one.
Okay. So the
And,
cipher manifold.
and there's another example of three manifold satisfying this one, but we do not know the full classification of three manifold, such as three manifold. This is open question.
So you just experimentally find this class.
Yeah, so in this example, I expanded upon that this all class satisfies this topological criterion. Yeah.
Okay. So this is
And
experimental observation
yeah,
by explicit computation.
And the partially mathematician proved that some part of this manifold satisfy this condition mathematically,
Okay.
and we checked that numerically that the but we don't know what kinds of the three manifolds satisfy this condition.
Okay.
We don't know
Okay.
the classification.
Okay, thanks.
So this is 3D relation for this one. And this dictionary can be easily obtained by comparing for general results for this topological field theory and this 3D relation. And there is a very nice match, and we can analyze that. We can identify the anion to be the related Fleck connection, and this S0 alpha part to be the torsion part, and this T part is this as in this way we can identify this one. And the trivial anion can be identified using this SL2 structure, which is expected to in the topological phase. So from this one we can study this one. And as Satoshi mentioned, this only determine first column of the S matrix, but to obtain the full S matrix, we should study the Fleck connection to loop operator map. So I briefly explained what is this map. So as I mentioned, that the anion has two interpretations on topological field theory. One is that can be regarded as a ground state on torus. On the other way is that it can be regarded as a type of loop operators. In terms of 3D correspondence, these ground states are related to the vacuum on the internal 3D manifold, which is given by the Fleck connections. So in this map, we can identify that this anion as the related to Fleck connection. On the other hand, this anion can be also identified the type of loop operators. But in 3D correspondence, this loop operator can be obtained by some intersecting M2 branes with the M pi branes. These are labeled by choice of the internal cycle, A alpha, and the number of M2 branes. So we can interpret this anion as intersecting M2 branes. So sometimes it is called Codimann's fourth effect of Tokuma-Zero theory, which is labeled by the representation of the SU2. As representation of SU2 is determined by this number of n. So from this two interpretation, we expect that there is a natural web between the Fleck connection and this Codimann's fourth effect labeled by A and choice of A alpha. And there are some condition to determine this map. And once we determine this map, then we can compute the full S matrices. These are the basic logic. And, I will skip the full details. Since a low time. So one interesting is that using this dictionary, we can determine the full modular structures of a topological phase associated with this three manifold. But then some cases topological phases are unitary in a sense that this S matrix satisfies this condition. Then we will claim that this for this case we will interpret that this TM theory has mass gap and flow to the topological field theory describe this unitary topological theory. But some cases, surprisingly, this resulting topological field theory sometimes is non-unitary. So if you compute this S matrix, it does not violate these conditions. Then our interpretation of this case is that this TM theory actually is flow to the Capital theory with the accidental U1 symmetry. And we will flow to the CFT with the U1 flavor symmetry. And this topological, non-unitary topological phase appears as some subset of this unitary CFTs. This is somewhat similar to the appearance of a non-unitary VOA in the subset as a subset in the unitary n equal to CFTs. So for given three manifold satisfying this criterion, then we can read of this modular structure. that depending on whether this modular structure is unitary or non-unitary, we can give two different interpretations. When this modular structure is unitary, it means that this is a capital pace and described by topological pace. Non-unitary, then this has a different interpretation.
Sorry, do you fix the Chern-Simons level here?
What Chern-Simons level?
Level, yeah. In the
Level?
right-hand side, for example.
Right-hand side?
Yeah.
To compute the distortion?
Yeah, for example, yeah, or H
Yeah,
alpha.
so this is defined by in this formal way. So this is something like a Chern-Simons level.
Yeah.
This is a formal parameter, and we can do the formal perturbative expansion.
So large K, you are saying?
Yeah, large K, and then the classical part and the wonder part.
So are you saying that the right-hand side doesn't depend on K in some sense?
Yeah,
I mean,
this right-hand side is some coefficient of the 1 over K coefficient. So this is a Chern-Simons function is the leading part of the K equal infinity limit, and this is one part of that one. So this is a K independent.
but in the previous some table, you are saying that yeah, level 1 ampere or something like that, right? Yeah, some I don't know the some table, right? You show something. Yeah, this
no,
one. Yeah,
that's TFT size.
Yeah, TFT size. Yeah, this is
it's a modular tensor.
If you consider three manifold, is a classification topology page, and this this is the topology page. So this topology page is described by the SO7 Chern-Simons theory level 1, something like that.
And so my question is, this level does not. Is there any counterpart in this 3D correspondence?
In three manifold, if we change the topology of a three manifold, then the resulting theory will be different. So the changing of Chern-Simons level theory of a topological pace, it corresponds to changing a topological pace. So it means that if we change some topological different shape of a three manifold, then you can change the Chern-Simons level resulting topological theory.
Can you say explicitly what's that counterpart of this level?
Yeah, it is not that simple. It is not that simple. So yeah, it is not that simple. If we fix the three manifold and then we obtain the resulting topological theory, then the topology theory can change the labeling and it will correspond to changing topology, but it is not obvious how to change the Chern-Simons level to in this.
I see. Thank you.
So let me give a concrete example. As I mentioned, this is manifold. This is infinite class of manifold satisfying the topology criteria of this all the irreducible Planck functions are real. And another thing is that the Chern-Simons function and the Chern-Simons term and the torsion part of this Planck connection for the manifold are known by mathematicians. So we can use this formula for given solution for this one Planck connection equation, then we can obtain this Chern-Simons functional and torsion automatically using this formula. So for example, if we choose that this manifold, so P1 and Q1s are chosen by 3 and 3 and this one, and as I mentioned, there's only 3 irreducible Planck connections, which correspond to 3 anyons in topological pace. And if you compute the Chern-Simons functional for this Planck connection, and this is given by this one. And if we compute torsion, and this is given by this one for each Planck connection. And using the dictionary that this topology spin of these anyons are related by the Chern-Simons connection functional in this way, then we can read up this topology spin of these anyons, and we found that these topology spins are 0 and this one and this one. And this is there are 3 anyons, so this is the level length TQFT with the anion spectrum is like this one. Then we can compare the classification table, and then we can find that this anion contents are exactly the same as the one of topological pace classified in this series in the Xiaoguang's papers. So this in this paper, there's a 5 length. There are 6 length 3 topological pairs, and this annual contents are exactly the same as this one. And these topological spins are defined only in mode 1, so these contents are actually the same as this one. So we can conclude that this topological pairs associated with this manifold is actually this topological pairs. And we can also compute the full S matrices, and then we can confirm that this S matrix also matches with the S matrix for this topological pairs. And this manifold can be realized in this way. The picture is not with some 3 surgery. Then using this, then it can be decomposed into 2 ideal tetrahedron and 1 solid torus. Then from this algorithm, we can also construct this effective field theory, which is given by this one. So this effective theory will flow to this topology pairs at the IR. This is the claim. And one can check that by directly computing supercompound index, one can check that this supercompound index actually become 1. There's no Q dependency. This is and then we can scan all the 3 manifold on this type, and they found that we can reproduce all the bosonic topology pairs classified in this paper up to length 4 using this manifold. As we relate to this switches question, so if we here is that these 2 theory, where is that these 2 theories, A15 and A17 are related by some changing of the Chern-Simons level, and then the resulting 3 manifold is this one and this one. So it is not obvious how to relate this changing of the Chern-Simons level to the topological manifold.
I see.
So yeah, anyway, so by scanning this manifold, then we can reproduce all the bosonic topology pairs using this algorithm. But in this cases, we consider these cases as 3 times this one. And in this case, we can analyze also modular structure. And it turns out that it is non-unitary. And this theory have 4 irreducible connection, and we can compute the Chern-Simons functional and torsion. And then we can found that this is actually non-unitary topology pairs. That how is this possible? We start from the unitary 6-2,0 theory compact pi 3 manifold, then how can we obtain this non-unitary TQFT? To answer this question, we carefully analyze the effective field theory description of this manifold. And this manifold can be triangulated by 3 tetrahedron and 1 solid torus. And the resulting solidity theory is given by this one. U1 theory coupled the 3 chiral, which has S3 times U1 symmetry. And then we gauge the SO3 subgroup of S3, SO3 subgroup of S3. Then this is corresponding theory for this one. This theory has some accidental U1 symmetry, which corresponds to U1 topological symmetry. So if we compute this supercompound index for this theory with turning on this fugacity for U1 symmetry, then we found this one. And then if we turn on this fugacity, then we obtain this index become the 1. Then our interpretation is that this theory actually flow to the CFT with the U1 Flavor symmetry, which is supercompound index given by this one. But if you specify some certain degenerate limit, U equal 1 limit, then this theory will contain this non-unitary TQFT as a subsector. So this is our interpretation. So this theory is actually flow to some supercompound field theory, but it contains some non-unitary TQFT as a subsector, and the modular structure we lead off is actually the modular structure of this non-unitary TQFT. This is our interpretation. And then we can actually check that for many other examples of the 3 manifold, which keeping this non-unitary TQFT, one can check that this always have a U1 symmetry in the effective field theory description. So this picture seems to be correct.
A question here. Is this U1 symmetry always from this accidental symmetry?
Yeah, I call this as an accidental symmetry because it is not invisible in the compactification of 2,0 theories. compactification 2.0 theory on 3 manifold, expect there's no abelian symmetry. But if you see this effective field theory description, then it sometimes have a U1 symmetry which is manifest in the effective field theory description. So in this theory description, there is a manifest in terms of effective field theory description, but this is not manifest in the 62.0 compactification.
Okay, thanks.
Yeah. So I call this is accidental because it is invisible from the empire brain picture, but this is not accidental in terms of the effective field theory because this is a manifest in this field theory description. So this is a summary of our result that we will answer that these questions to using this table when this three manifold have a trivial Z2 homology, and the corresponding theory is a bosonic T-cavity with a modular structure is given by this one. And there's also interesting story for the non-trivial Z2 homology, and which is studied by these people in terms of 3D correspondence. So one crucial thing is that in these cases, there are some variant of the discrete variant of 3D theory, and this 3D theory is actually labeled by the M as well as a choice of a subgroup H. So different choices of this subgroup are related by each other by the one-point gauge symmetry or discrete one-point gauge symmetry gauging or the zero-point gauge symmetry gauging. So I cannot go into detail, but the one crucial thing is that this Z2 homology of the homology of this internal manifold play role as some one-point symmetry or zero-point symmetry of this resulting 3D theories. So in the condensed method theory, this gauging one-point symmetry is called the anion condensation. So this discrete choice of different choice of 3D theory are related by the anion condensation on gauging. So some cases through this anion condensation, we can obtain the fermionic topological phase, which is spin T-cavity. So in this way, so we can geometric engineering give us not only the bosonic topological phase, also some fermionic topological phase, as well as a non-unitary topological phase. So this geometric construction give a unified framework for bosonic, fermionic, and the unitary non-unitary topological phase. So I'm running over time. Let me summarize my talk. So this is summary. So for three manifold with certain satisfying certain topological criteria, we claim that this theory will flow to the topological phase. And then we will give some explicit algorithm of extracting the modular structure of topological phase geometrically from the topology data of internal three manifold. And we also give an effective supersymmetric description for this topological phase. And also we give some embedding of a non-unitary T-cavity in some unitary CFTs. And this provides unitary framework for topological phase. And there's a lot of interesting future directions. First, in our study, we only can reproduce the modular structure of this topological phase from geometrically, but there is additional data beyond the modular structure to define the topological phase. So we don't know how to identify this additional structure from geometric side. And in this talk, in my talk, I only scan the three manifolds labeled by three fractional number, but there could be another three manifolds that find this topological criteria. We don't know the full classification of such a three manifold. And also it is interesting to generalize it to some higher rank of the theory, which is by increasing number of empire brains. And using this one, maybe we hope that we can find some exotic capital phase, which is not studied in the literatures. And another interesting thing is that from this topological phase and geometric correspondence, we can relate the physics of topological order to the mathematics of a non-hyperbolic three manifold. For example, that by requiring, we know that there's only one ground state on the S2 for topological phase, then it can be translated to some mathematical non-trivial identity on the three manifold side. And another universal property of a topological phase can be translated to non-trivial mathematical identity on the topological phase. Thank you for your attention. Sorry for running over time. Yeah.
Questions? I think.
Okay. How about other space-time dimensions?
So you mean the 4-dimensional or 2-dimensional space-time dimension?
Yes.
Yeah, so 4-dimensional cases that, yeah, we can also study similar things. So we may start from some supersymmetric, some gauge theory, and then maybe some of them will flow to the gapped phase. Then using some localization technique developed recently, then we can try to lead up to this gapped phase, which topological phase. But unlike the 3-dimensional 2+1D cases, the basic structure of a topological phase of 3+1 dimensions are not well understood. For example, that 2+1 dimensional topological phase, basic physical observers are loop operators. And if we compare to all the correlation function of loop operators, then we can solve the topological phase. But in 4-dimensional cases, 3+1 dimensional cases, not only loop excitation, but there is a surface-like excitation exists in the topological phase. And there have some relation between this excitation correlation function and some other partition function. But as far as I know, not many things are studied in the 3+1 dimensional topological phase. Yeah.
So may I ask? So phi is S is the S matrix, right, of the modular matrix in the left-hand side. Phi S squared correspond to the this inverse of this Raysinger torsion.
Yeah. So this is because that yeah. So this is hidden in the 3D correspondence at yeah. So this is a basic region. So as I mentioned that this is 3D relation.
Yeah. Yeah. Yeah.
And this is a general factor on the topological phase.
Right. The bottom line is coming from that this just 2D. I think this gluing of the solid torus and. Do you understand the reason why this torsion part is one loop, right, of the localization? And why does this depend on this S matrix? That's what I want to know.
Yeah. So yeah, this is so quite non-trivial. So the reason, technical reason is that using 3D relation, I found this relation, general relation.
Mm-hmm.
And then I compared this general relation for topological phase, and this should work match for the arbitrary G and the arbitrary P. Mm-hmm. And the only way that both sides can match is that this should be equal to this one and this should be equal to this one. Mm-hmm. Yeah. So another thing is that how to derive this 3D relation. Mm-hmm. So how to derive the 3D relation for this partition function on this Euclidean background? Yeah, that's quite non-trivial, and this is studied by quite recently, yeah, by myself and my collaborators. Yeah, so I think that this derivation is quite non-trivial.
I see.
Although final answer is very simple, but yeah, derivation is very somewhat messy. So yeah, so we should use some explicit description of this theory using ideal tetrahedron gluing. Then we apply the localized technique. Then we obtain some expression. And there's another expression using the ideal tetrahedron. Then we can compute the torsion of this Chern-Simons functional. Then the expression, them are matched. So yeah, so derivation is quite matched, and the final result is very simple. So yeah, then if we accept that, then you can easily see that this dictionary can be easily derived from this relation.
So 3D correspondence, this Z correspond to the in the other 3D theory, right? This
yeah,
Z.
so yeah, 3D generally said that the partition function of TM theory on curved background B is related to some invariant depend on the curved background over SL2C consignment theory on the M.
Okay, and the right hand side of this bottom equation, the one, yeah, this one. So right hand side derived by the upper conjecture is this invariant B of SL2C. Is that right? Or I mean, how? So my question is, how do you derive this equation by using conjecture or not?
No, I'm derived just the honest
computation of this.
I compute the left-hand side using the effective field theory description and the localization, and I compute this one using some mathematical technique, and I compare these two expressions and they match.
Okay, fine then. And so you don't use 3D correspondence here.
So this is 3D relation. I derived it using the direct computation.
Wait. No, my question is, do you use 3D relation? Where do you use 3D relation?
Our derived 3D relation.
So to obtain a T of M theory, you need the 3D correspondence. T of M theory is a 3D n equal 2 theory. Coming from 3 manifold M. So to obtain the physical theory, T of M theory, you need to use 3D correspondence. And then to evaluate the partition function on S1 cross sigma G, you need a localization. Then he got a distortion times.
Oh, I see. So I see what you mean. So okay, you did two computations here. And you are saying the these results match. That's your statement in this.
Yes. So,
okay, I understand.
Left-hand side, we know some 3D-dimensional description, effective description of this theory, and I compute the partition function using localization. We won't have one expression, and then on geometric side, there is a mathematical way to compute the distortion and this Chern-Simons invariant. General method is based on ideal triangulation and solid torus gluing. Then I compare two expressions and they match. This is derived firstly in this paper, and later, so with the paper with another paper, I give some simpler derivation of this 3D relation, but that is also somewhat messy.
Okay, then could you go one ahead slide? One ahead, and this so. Sorry, one more ahead. Sorry, one more ahead. I think you wrote some relation, right? 3D. I mean, what I want to ask is, can you how should I say?
This one?
No. I mean, so I mean, do you need this 3D relation to derive this 2D, I mean, the topological phase? I mean, does it make sense? How should I say? Is this necessary? 3D relation is necessary to derive this?
Yeah, it's very necessary because that I derive this dictionary using this. I call this a 3D relation.
So it but I mean lawyer one is somehow, I mean, familiar. Lawyer one is familiar.
Yeah, it's a general.
Right? This is some gluing of the, I think, solid torus kind of thing, which is clear. But the upper one is
upper one is quite non-trivial.
Yeah. So I want to understand which predicts from the lower one. I mean, that's what I want to know. I mean, lower one is okay, but
upper one is So this is after I obtained this relation in this which paper? This paper. So this relation is generally true for general three manifold, and this relation is only valid for when the 3D. This is valid for generally valid for this topological case.
Okay, I
And
think
then
the further question can be, postponed to the informal discussion. So let's thank the Domi again, or by whatever method. Okay, I will switch off the recording and.